This lecture is about Coulomb's law for electrostatic force. We have electrostatic charges, and the charges may attract and repel each other. Now the question is, if they are attracting, repelling, then at what distance and what magnitude? This is discussed by Coulomb. This lecture is about basics of Coulomb's law, then its vector form and numerical applications. The Coulomb force between two or more charged bodies is the force between them due to the Coulomb's law. If the particles are both positively or negatively charged, the force is repulsive. But it means if they both are same charged, then the force will be repulsive. But if they are oppositely charged, then it is attractive. The Coulomb's law gives you the idea, gives you the formula to calculate the things. It is again a kind of law that is given by Newton, that is gravitational law. By the middle of 18th century, only the qualitative aspects of the electric force were known. And the scientists started to speculate about qualitative aspect of the force and the idea that the electric force could be similar to gravitation force. They tried to obtain the results that similar means that this force again may be proportional to inverse of square of that distance. Yes, that is right. These two, both of these laws are square laws. The electrostatic force and gravitation force. However, the biggest difference between these two is this is charge dependent, where gravitation force is not. Gravitation force is always attractive, but here, as it is charge dependent, it may be attractive or repulsive. In the end or of the century, 18th century, 1785, Coulomb proved experimentally that indeed the electric force are proportional to the inverse of the square of the distance between them. This is one of the greatest discovery of that era. Coulomb has given a statement, and that statement is, if you are having two electrically charged bodies, then the force between them is proportional to the product of module of their charges. However, this force is inversely proportional to the distance, square of distance between them. So you can even write these two things separately if you want. The F is proportional to Q1, and Q2. Similarly, F is always also proportional to, these are the observations given by Coulomb dt square. If you combine these two, then you will get the result as this. F is proportional to d q1 q2 over d square. Obviously, if you use this, change this sign by equal sign, then you will also observe one proportionality constant, that is called k here. This law is called Coulomb's law, and this was the first attempt to understand electric force like gravitational force. Gravitational force was studied in 17th century by Newton, and then in this 18th century Coulomb studied the Coulomb force. The Coulomb force is and gravitational force both are inverse square law. Unlike the gravitational force, the Coulomb force may be either attractive or repulsive depending on sign of the charges of Q1 and Q2. So this is the basic difference between these two. The Coulomb may be either attractive or repulsive. However, as we know that gravitation is always attractive. As we have used the constant of proportionality k, this depends on choice of unit used. In MKS system of units, the constant of proportionality is called Coulomb constant. This force looks like the law of universal gravitation, which deals with attraction between objects with mass. The difference is any two charges experience mutual attraction. The two charges can either be, however, charges can either be attract or repel. This depends whether the sign of their charges are like or different. As it has been seen in the picture, we have two charges Q1 and Q2, and the distance between these two charges is R. So if this is Q1, Q2 and R, we can calculate the force Q1 Q2 upon R square, and of course K, the proportionality constant. Now if the charges are like the same, then this will repel each other. This will go in opposite direction, this will go in opposite direction, force will be. However, when charges are opposite, unlike, then it will attract. The force is same. As we do with the gravitation and all other kind of forces, Coulomb force add as vectors. Thus, to find the force on a charge from arrangement of charges, suppose many charges are there, one need to find the vector sum of the forces from each charge. Suppose there are n number of charges and applying a force on a test charge, then the all charge will be total force will be F, that is sum of F1 plus F2 plus F3 and so on. Now the physical quantities are of two types, scalar and vectors. And we know the force is a vector quantity, so we can also write the vector quantity form of this Coulomb's law. Vector have both magnitude and directions, whereas scalars have only magnitude. The law that we have discussed in the previous slide doesn't have any direction, representation of direction. So we have to add the representation of direction in this. The Coulomb law can be rewritten in the form of vectors. Suppose there are two charges Q1 and Q2 and their position are R1 and R2 respectively. Since both the charges are of the same sign, there will be repulsive force between them. Suppose we assume that the force on the charge Q1 due to charge Q2 is F12 and the force on charge Q2 due to charge Q1 is F21, then the corresponding vector form will be Q1 to Q2 is R21 vector. So R21 actually is a vector that is R2 minus R1 and force is F21. Now, to denote the direction of a vector from position vector R1 and R2, actually R1 and R2 are the position vectors. We use a vector notation R21. That R21 is R21 cap is a unit vector and R21 this is equal to R21 over R21 where this is the magnitude of this vector. From here we can calculate the unit vector. Actually this lower one is the magnitude and upper one is the vector. Suppose this is Q1 and the second one is Q2. Then this unit vector is R1 and the second vector is R2. And we are talking about R21 and R2 which is here. R12 and R21 will be delivered by here. It depends on whatever we want to calculate. Now the force on charge Q2 due to Q1 can be written as Q2 due to Q1 can be written as F21. This is 1 upon 4 pi epsilon 0 Q1 Q2 upon R21 square. And with this unit vector. The unit vector is used because on the right hand side you are using vector quantity, but on the left hand side you are using vector, but on the right hand side the quantity is not vector. To add this vector notation, we have used R21 here. This is called vectors form of Coulomb's law. The vector form of the equation is independent of size of both the charges, as both the forces are opposite in nature. The repulsive force F12, that is the force on Q1 due to Q2, and the another force F21, then the force on Q2 from Q1 are opposite in sign due to change in position vector. And so F212 is equal to F minus F21. This is because the position vector in case of F12 is R12 and position vector in case of F21 is R21. And we know that R21 is equal to R2 minus R1 and R12 is equal to R1 minus R2. Since both are opposite in sign, they make forces of opposite sign too. It is proved that the Coulomb's law fits into Newton's third law. Every action has equal and opposite reaction. And that is why it also holds this property. Coulomb's law provides the force between the two charges when they are present in vacuum. This is because charges are free in vacuum and don't get interfere from other matter, air or particles. So Coulomb's law gives the charge may be in vacuum. However, there are certain limitations of Coulomb's law. We will discuss these limitations one by one. We have this law is limited to the following points. This law can be used when the charges are at rest. This law is only for static particles. If the charges are moving, cannot give you answer. So that is important. It can be used only for static particles. For moving particle, we have different laws. As the charge is moving, then it will also generate current. It may also give uh, magnetic field. So the different complex events are there. It is easy to use while dealing with charges of regular and smooth shape. And it becomes too complex to deal with charges having irregular shape. Because all the time you have to calculate distance between the charges. So if the shape is regular, then it is easy to calculate. But if the shape is not regular, it is not easy to calculate. And that is why we have moved to Gauss law to calculate electric field for large number of charged particles. The particles are less in number, then this can be used, but the charge are more, then it is difficult to work with Coulombs. The formula is only valid when the solvent or molecules between the particles are sufficiently larger than both of the charges. If the solvent molecules are less than this, then it may interfere the results. So these are the limitations